All right, let's talk about one of the biggest headaches in modern software, getting all of your different microservices to actually talk to each other without everything catching on fire. We're going to dive deep into gRPC, and I promise, by the end of this, you'll see how it can take that messy spaghetti code and turn it into a clean, contract-driven work of art.
Okay, let's just get real for a second. You've just built this amazing new service. It's elegant, it's perfect. But now you have to connect it to 5 other services. Suddenly, you are drowning in boilerplate code. You're digging through docs trying to figure out what some vague field in a JSON payload actually means. You're handwriting serialization logic, and you're basically just praying that the team on the other end hasn't changed their API without telling you. Seriously, why does this have to be so hard?
I hear you. Trust me, we have all been there. That old manual way of doing things with REST APIs, it's just so fragile. You're relying on documentation that, let's be honest, is probably out of date the second it's written. But what if we could flip that whole idea on its head? Instead of hoping our code matches the docs, what if the code was automatically generated from one single crystal clear contract? Well, that's the gRPC way. It gives us a single source of truth, super efficient communication, and, this is the best part, it writes all that tedious, boring boilerplate code for us, making sure everything is type-safe right from the very beginning.
So the absolute foundation of any solid gRPC system is the contract. And I'm not talking about a page on a wiki or a comment in your code. No, this is a dedicated file that defines everything about how your services communicate. And it's all written using something called protocol buffers. So what exactly are protocol buffers, or protobuf for short? The easiest way to think of them is as the blueprint for your data. It's a language Google came up with to define your message structures and your service interfaces. You can think of it like a universal translator for all your services, except it's one that's incredibly fast and efficient because it serializes everything down to a super compact binary format. And just look at how simple and readable this .proto file is. We're defining our data structures using the message keyword. So our numeric request has 2 integers, v1 and v2, and our numeric response has 1, r. Then we define our actual API using the service keyword. Our test service has a single remote procedure call, or RPC, called add. And it states, clear as day, that it takes a numeric request and it returns a numeric response. There's just no ambiguity here at all.
Okay, so we have our contract. Now, for the really cool part, the magic. We are not going to write the networking code, we're not going to write the serialization, we're not going to write the client libraries ourselves. We are going to generate all of it with a single command line tool called protoc, the protobuf compiler.
This one little command, this is the key to everything. We're just telling the protobuf compiler, protoc, hey, take our add.proto file and generate all the Go code we need for gRPC. It reads our contract and just spits out all that complex, error-prone glue code that we all used to have to write by hand.
So what do you actually get from that command? Well, it writes the Go structs for our messages, but then it creates a test server interface. Think of this like a checklist. It forces our server to implement that add function correctly. And on the other side, it gives us a test client stub, which is a pre-built library for calling our server that's completely type-safe. You literally can't even call it with the wrong data types. The compiler just won't let you.
Okay, we've got our contract and we've got our generated code. Now it's time to write our actual application logic. And you are going to be shocked at how little code it takes to actually connect the client and the server.
So the whole thing boils down to this simple 4-step workflow. First, you write the proto contract. Second, you generate the code. Third, you implement the actual business logic on the server. And fourth, you write the client to call it. This cycle is fast, it's repeatable, and it is so much less error-prone than the old way.
I mean, just look at this server code. Isn't that beautiful? All we're doing is implementing the add method from that interface Proto gave us. Notice what's missing? There's no networking code, no JSON parsing, no boilerplate, nothing. We just take the numeric request object, we grab its fields v1 and v2, add them together, and return a numeric response. That's it. This is only our business logic.
And the client side is just as clean, just as simple. We use the generated new test client function, and then we just call the add method as if it were a local function in our own code. We pass in our numeric request struct, and we get back a numeric response. It is simple, it's direct, and the compiler guarantees that v1 and v2 are integers. You can say goodbye to those nasty type mismatch errors at runtime.
And right here, this is the real superpower of gRPC. Remember, we defined that .proto contract just once. Our Go client calls client.add. A Node.js service can dynamically load that exact same file and make the same call. A Ruby service generates its own client from that same file and calls stub.add. The language is totally different, but the contract, the conversation, is identical. This is how you build a robust, polyglot microservices architecture that actually works.
Okay. Adding two numbers is a great start, but we all know real-world APIs are way more complex than that. So let's see how Protofile handles more advanced data structures, like lists and enumerated types. Let's upgrade our API a bit. First, we're going to define an enum. This lets us create a set of named constants, which is so much safer than just passing around magic strings or numbers that nobody understands. Second, notice that little repeated keyword. Just by adding repeated before int32, we've now defined values as a list of integers. The generated code will automatically turn this into an array or a list in whatever our target language is. It's really that easy.
So far, we've really been focused on direct, synchronous calls. The client calls the server and then just sits there waiting for a response. And that's great for a lot of things, but in a large distributed system, it has a pretty critical weakness.
So let me ask you this. What happens when your client makes that add call, but the server is crashed, or it's temporarily offline for deployment? The call fails. Yeah, the client might retry a few times, but if the server is still down, that request is just gone. It's lost forever. And in a real system, that is a huge problem.
And that brings us to a really crucial design principle for building resilient systems. Synchronous requests are not durable. For any kind of critical task, a much better pattern is to introduce a durable queue. The client doesn't call the server directly anymore, it just adds a message, a piece of work, to a queue. And then some worker service can come along and pick up that message and process it whenever it's ready.
Now, the really cool thing is, we don't have to throw away everything we just learned. We can map these gRPC concepts directly to a queuing system. So an RPC call becomes an enqueue message operation. The gRPC server becomes a queue consumer or a worker. The typesafe client becomes a typesafe producer. And most importantly, our .proto file is still the single source of truth for the message contract.
And this is just incredibly powerful. You get to reuse all your protobuf definitions. You get a type-safe producer that makes it impossible to put the wrong kind of message onto the queue. Your consumer on the other end is also type-safe, implementing the same kind of service interface we saw earlier. And once again, you get to avoid all the boilerplate serialization code and just focus on the important part, the business logic for processing that task.
So, we've seen how gRPC and its whole contract-first philosophy can totally clean up our service communication, make it type-safe across different languages, and even inform how we build more resilient, asynchronous systems. You have the tools now. But I'm going to leave you with one final thought to chew on. Your services can now talk to each other flawlessly. But are they having the right conversation? Are your service boundaries and your contracts actually designed to build a truly robust system? That, my friends, is the next level. Thanks for joining me.